Dear students, so today I tell you about some concepts in complex analysis. So, singular points of an analytic function. Singular points of an analytic function. So now here, as you know that a function f of z is said to be analytic if its derivative exists at all points in a region R. Okay. So singular point means what? It is a point at which the function f of z ceases to be analytic. Ceases to be analytic means what? It is a point at which the function is not analytic, or the derivative of the function does not exist. Does not exist means what? If you find the derivative at that point is infinity. Okay. So here a point z is equal to a is said to be singular point of a function f of z if the function f of z ceases to be analytic. Means the derivative of the function at this point does not exist. Ceases to be analytic. For example, consider the function f of z is equal to 1 divided by z minus 2. Consider a function f of z is equal to 1 divided by z minus 2. Okay, now we find its derivative. So what is f dash of z? F dash of z is, so it is minus 1 divided by z minus 2 whole square. Okay, so by applying quotient rule and all that, so we find the derivative, that is minus 1 divided by z minus 2 whole square. Now see here, when you substitute, put z is equal to 2 in this case. Then what is the value of f dash of z? Then f dash of z becomes 1 divided by, that is 2 minus 2 is 0, means it is infinity. So at z is equal to 2, the derivative of the function becomes infinity. Or we can say that at z is equal to 2, the derivative of the function does not exist. So z is equal to 2 is a singular point of the function f of z. So therefore z is equal to 2 is singular point of f of z. Okay, so this is one example. Next I'll give another example. Take 1 divided by, now consider another example, f of z is equal to z divided by z minus 2 whole square. Okay, again find its derivative. So f dash of z is equal to, now see here, f dash of z is equal to, again when you differentiate these things, you will get, by applying quotient rule and all that, in the denominator we see z minus 2 to the power 4, right? So at z is equal to 2, again the function is, the derivative of the function does not exist. So therefore z is equal to 2 is a singular point of the function f of z, that is z by z minus 2 whole square. So similarly here, f dash of z is infinity at z is equal to 2. So therefore z is equal to 2 is a singular point of f of z. Okay, so this is about a singular point. Next comes isolated singular point. Next we have isolated singular points. Isolated singular point. Okay, so isolated singular point means what? A singular point z is equal to a is said to be isolated singular point if there exists a circle with z is equal to with center a such that it has no other singular points. Okay, so that is, for example, take example f of z is equal to z divided by z minus 1 whole square. Okay, now when you differentiate this, f dash of z is equal to what is its differentiation? Z minus 1 whole square into differentiation of z is 1 minus z into differentiation is 2 into z minus 1. Again by applying chain rule, z minus 1 differentiation with respect to z is again 1 whole divided by z minus 1 raised to the power 4. So by applying quotient rule we will get this one. So f dash of z is equal to, how much we will get? So this is z minus 1 whole square minus 2z into z minus 1 whole divided by z minus 1 whole to the power 4. Now at z is equal z minus 1 whole square, don't take z minus 1 whole square, take z square minus 1, take example of z divided by z square minus 1. Okay, z square minus 1. So now in this case, now see here, when you substitute z as plus 1 or z is equal to minus 1, so then we'll get denominator term as 0. So z is equal to plus 1 and minus 1 only for these values, only for z is equal to plus 1 and z is equal to minus 1, this denominator terms gets 0. So there are only these singular points and no other singular points. Only for these values of z plus 1 and minus 1, this f dash of z is going to be infinity, or the derivative of the function does not exist for only these values. So therefore there exist no other values, no points other than 1 and minus 1. So therefore this z is equal to plus or minus 1 are called isolated singular points. They are called as isolated singular points. Okay, so another example I will give. Say f of z is equal to 1 divided by sine pi z. F of z is equal to 1 divided by sine pi z. Now find out its derivative, f dash of z. So actually what is 1 by sine pi z? It is cosec pi z, right? So differentiation of cosec pi z is minus cosec pi z into cot pi z into pi, right? Into pi. This is f dash of z. Or we can write f dash of z as, so minus f dash of z is equal to minus cosec pi z, we can write that as 1 by sine pi z, and cot pi z as cos pi z by sin pi z, cos pi z by sin pi z, and remaining thing that is pi as it is. Okay, so now this is equal to, now f dash of z is equal to minus pi into cos pi z divided by sin square pi z. Okay, so now when you check value for z is equal to, for if you take z is equal to 1, then it gives sin pi, so sin square pi or sin pi whole square. So for z is equal to 1, it gives sin pi whole square, so sin pi value is 0. Then if z is equal to 2, again sin 2 pi value is also 0. Okay, so sin, again when you take z is equal to 3, sin 3 pi is also 0. So sin pi, sin 2 pi, sin 3 pi, sin 4 pi, sin 5 pi, so sin 6 pi, so sin n pi for all n, so it's equal to 0. Similarly, if you take z is equal to minus 1, again same thing you will get, but only the thing negative sign will occur. So that is minus sin pi, then minus sin 2 pi, minus sin 3 pi, minus sin 4 pi. So for all these values it gives 0. That means the derivative becomes infinity. The derivative does not exist. So for z is equal to plus or minus 1, plus or minus 2, plus or minus 3, then plus or minus 4, and so on, so on. So it becomes 0, and there is no other value, there is no other points other than these things. So therefore all these are isolated singular point. Isolated singular points. That means, see, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, and so on. There is infinite number of isolated singular points are there for this function. Okay, so this is about singular points of a function f of z. Now if z is equal to a is an isolated singular point, if z is equal to a is an isolated singular point, if z is equal to a is an isolated singular point, if z is equal to a is an isolated singular point, so then f of z can be expanded in Lorentz form. Then f of z can be expanded as f of z is equal to summation from n is equal to 0 to infinity a n z minus a whole to the power n, then plus summation from n is equal to 1 to infinity a minus n z minus a to the power minus n. So this expansion is known as Lorentz series. So remember that if z is equal to a is an isolated singular point, so then only we can expand f of z in this form. Okay, so then that is f of z, the right first term as it is, n is equal to 0 to infinity a n z minus a whole to the power n. Now expand this term using n is equal to 1, 2, and so on. So for n is equal to 1, it gives a minus 1 z minus a raised to minus 1. Next plus a minus 2 z minus